Okay, so my name is Malagò Luigi, and today I will talk about some recent work in collaboration with Goffredo Chirco and Giovanni Pistone about mechanics and geometry of a statistical manifold, and in particular, I will present a Lagrangian and Hamiltonian formulation for dynamics over a set of probability distribution. So this talk is a little bit different, I would say, from the previous one, which were mainly centered on robotics and geometry aspects playing a role in robotics. This talk is a little bit more general, focused more on geometric aspects coming from information geometry, but it has a direct application to optimization, and it goes in the direction of defining a framework which is used for the definition, for example, of accelerated dynamics over the probability simplex and more in general over statistical manifold. Okay, let me give you two motivations from machine learning and optimization so that we can define some terminology and we can make sure that we are on the same page. Let's consider two different problems. The first one coming from statistics is the maximization of the likelihood. So we are maximizing a function which is defined over a set of probability distribution, is defined over the parameters of a set of probability distribution given some observation, and so is a function of parameters. And the second one is the optimization of a function defined over a sample space, and is a stochastic relaxation, which means the optimization of the expected value of the function with respect to some probability distribution in a statistical model. So what is common between these two problems? Well, both of them are cases of optimization over a function, which is defined over the parameters of a statistical model. So if we introduce a statistical model M, which in our case is a set of probability distribution, it could be, for example, the simplex multinomial distribution for finite omega, it could be Gaussian distribution, the cone of positive definite matrices, and so on, depending on the setting. In general, we are solving a problem which is the optimization of a certain function, which is a function of P, and P belongs to M, where M is our statistical model. So this formulation here is implicit formulation. We didn't specify how to represent P, but if we introduce a parameterization, and so all the probability distribution belonging to the model are parameterized by a common set of parameters, we can reformulate the optimization problem as an optimization over the set of the parameters which identify the probability distribution. So how do you optimize this function? Well, in general, these functions are non-convex, so you do not have a closed formula solution for the optimum. So a naive approach, but still very powerful, is gradient descent, in which we optimize the parameters in an iterative way in the direction of the gradient. However, if you do this type of optimization, you may know that you may have some issues, for example, a dependence on the parameterization, and so different dynamics depends on the choice of the parameterization used to represent a statistical model. You may have slow convergence of a plateau, which are introduced not by the function itself, but the way in which the statistical model is parameterized. And in certain cases, the gradients need to be projected in order to point in the direction which give you a proper probability distribution, which may not be the case, for example, when you are close to the boundary of the domain of the parameters which represent your model. So most of the problems arise because we are using in this gradient descent update a geometry which is Euclidean. We're just computing the vector of partial derivative. However, we know from information geometry that the Euclidean geometry may not be the most suitable for this type of problems when you're doing optimization of a statistical manifold. And this led, for example, to the use of different metrics, for example, the Fisher-Rao metric, which is the one used in the natural gradient introduced by Amari, where the vector of partial derivative is pre-multiplied by the inverse of the Fisher matrix. This gives you, for example, dynamics which do not depend on the choice of the parameterization. You have acceleration in presence of plateau, so you do not have slow convergence. And the gradient always points in the direction of a proper distribution in the domain of the parameters of the model. Okay, so gradient descent, as we said, is a naive approach to optimization. Natural gradient, however, is used in many different fields. It has application in machine learning, statistics, signal processing, robotics, deep learning for the training of neural networks. And in general, for all the cases, and there are plenty of them when you are doing the optimization over a statistical model. We know from the literature that gradient descent can take advantage of acceleration, for example, momentum or Nestor acceleration. And recently there's been a lot of work in the direction of defining proper acceleration method in presence of a Riemannian manifold, in which we have a specific metric and a specific connection defined over our manifold. So here there are some references. We also have some references of recent work for Nestor of acceleration in continuous flows for natural gradient over probability spaces. So what are we gonna do? In this presentation, we aim to define a framework for accelerated natural gradient. In order to do this, we need to define a setting coming from information geometry, so a formulation and a framework where we use a notion of differential geometry, affine geometry, to describe statistical models. We also need to define a proper framework in which we can define classical mechanics over this manifold, and then we can define the Lagrangian and Hamiltonian, which allow us to have an interpretation connected to acceleration for our dynamics. So we will start with a brief introduction to non-parametric information geometry, which will tell us a little bit of notation and a proper setting for our framework. Then we will describe the mechanics of the simplens, so how to compute Lagrangian and Hamiltonians. We will then discuss KL Lagrangian, which is a specific case of Bregman Lagrangian. And we will introduce some example with a specific reference to an example in optimization. So this presentation is based on an archive paper where you can find all the details of the derivation that I will discuss in the next and some more examples. Okay, so classical mechanics is usually defined in finite dimensional Riemannian manifold. Here there are some references of classical monograph on the subject. Information geometry is a field in which we study statistical models using notion of differential geometry, differential Riemannian and affine geometries, and the field has been, most of the contribution in the field have been given by Amari, starting from the 80s, but there are also other people who work on the subject. Fisher and Rao had some preliminary work on the subject, which was fundamental for what has been exploited later on and presented later on. There are also some recent monographs that you can see. What is peculiar of information geometry is not only the use of a Riemannian metric for the description of the manifold of statistical distribution, but also the duality that we have between parameterization, between connection, which we will exploit a lot in the next. Some preliminary work in the direction of connecting classical mechanics and information geometry are the work of Pistone 2015-18 and co-authors, and also Leoc and Zhang 2017. So, at the beginning, if you remember, I mentioned an approach based on non-parametric information geometry. Non-parametric information geometry is a presentation of information geometry which relies on an implicit representation, a non-parametric representation of probability distribution, which is suitable when you want to extend the framework of information geometry to the continuous case, the infinite dimensional case. And the non-parametric information geometry has been introduced by Pistone and co-workers starting from 1995. In this specific presentation, we will talk about finite dimensional state space. Our dynamics will be defined over the probability simplest, but in general, the framework can be extended, and that's how it's been defined, with the purpose to be extended to an infinite dimensional space. So we wanted to study a relationship between information geometry, and so between notion of statistics and notion of Riemannian and affine geometry, and also classical mechanics, in order to define a correspondence between the quantities which are involved in both cases, and our purpose is to define dynamics, continuous dynamics of in the probability space, and this have application, for example, in the study of population dynamics, differential games, but also in optimization, which will be one of the main area of interest for us in this presentation. Okay, so let's start by introducing some notation. These are the basics of non-parametric information geometry. You can refer to some of the literature that I mentioned for more details. We need to define a maximal exponential family. So we start with a finite sample omega that in our case will correspond to a set of cardinality n. We have a probability simplex, which is the space in which our dynamics will be defined. And the maximal exponential family is the set of all the probability distribution which can be represented as exponential of a certain function. So it corresponds to the interior of the probability simplex. And in our notation, given a reference distribution P, any distribution Q can be expressed as the exp of U of x with a corresponding normalizing factor which allows the distribution to sum to 1. So using this notation, U can be expressed as the log of the ratio between our distribution Q and the reference P centered, which means that we remove the expected value with respect to P of the same quantity. Notice that all the set U have expected value 0 because, I mean, if we had a constant, basically the distribution remains the same, and so we have to, we can remove this degree of freedom by setting the expected value of the quantity equal to a constant, which we choose to be 0. Okay, so the second object we needed to introduce is the statistical bundle. The exponential statistical bundle is the set of points, vectors. So the manifold is made of a set of density Q. In each Q we have the possibility to define a vector, and this vector, as we said, has the property to be centered in Q, so its expected value is equal to 0. So the statistical bundle has also a dual space, which is a dual statistical bundle, which we will denote with star. In the case of finite omega, the two spaces correspond. What is very relevant, and this is something which is specific of our approach based on non-parametric information geometry, is the fact that we are identifying coupling between the tangent space and the cotangent space, so between the statistical bundle and the dual statistical bundle, given by the inner product between the two, the vector and the covector, basically, which is expressed as the expected value in the point of the product of the two. We can also define the transport on the statistical bundle and the transport of the dual statistical bundle. There are information geometry typically two transport of interest, the exponential and the mixture transport. The exponential transport is defined as the centering, so when we move a distribution to another one, we recentered the we recentered V in the point such that the expected value of the new quantity is 0, and the mixture transport, which is defined by duality, is obtained by multiplying the vector through by a ratio. So the two transport are in duality. So transport move vectors between tangent space defined in different points. So these are properties of dual transport which are well known in information geometry. So basically you can move a point from a vector with a transport and the other with the other dual transport, and the inner product remains the same. Similarly, you can move the two vectors with the dual transport, and this will maintain the inner product between the two quantities. Okay, so now another piece is given by the exponential atlas, which is a set of all the possible, the collection of charts that we have that allow us to represent our points. In this case, we given a couple QV. Q is a point, V is a vector. We use SP, which is the representation in the chart of our distribution, and we use the transport to represent the vector in the chart. we say that the chart is centered in P when we are representing our vector with respect to the distribution P in the point. Notice that by some properties of this construction, it can easily be seen that there is a correspondence between the cumulant function, which plays the role of normalizing factor in the exponential family, and the divergence between P and Q. By inverting the chart, we can find the patch, which, given U and V, allow to represent them in their parameterization. Okay, so similarly, in a pivot case, we have solved the dual atlas, which corresponds to the mapping with respect to a different transport for the vector W. In this case, in the dual, we use M, which is the Mishnah's transport. And similarly, also in this case, we can invert the transformation in order to define the patch. Okay, so statistical manifolds are a special case of Hessian manifold, so they inherit a structure which is very relevant for the duality between the parameterization, the mixed parameterization, the exponential parameterization, also the duality of the transport and all the other alpha connection duality which is typical of information geometry. And in this case, statistical manifold, a Hessian manifold, implies that there exists a parameterization such that the metric can be expressed as the Hessian of a convex function. In the case of the exponential family, if we take the normalizing factor and we express it as a cumulant, we take the second order derivative and we obtain the metric we obtain the metric in the parameterization of the natural parameters. This is one of the property of statistical manifold. Besides that, there is also the possibility to introduce a dual parameterization to define the recentering by removing the expected value, and we can also define third order cumulant, which are useful for the construction associated to covariant derivative and the Christoffel symbols. Okay, so we want to talk about mechanics, so we need to introduce velocity. So let's take a curve. A curve is a set of points which depend on t, and then we have vectors defined along the curve. We want to represent our curve in the exponential chart, so we use SP to represent the point, and we use the parallel transport in order to represent the vector in the chart. And by taking derivative, we can basically define, give a formula for the velocity vector. So we take the derivative over time of the representation in the chart of our point, and by doing some calculation, we see that this corresponds to the transport of the derivative of the log probability. And the derivative of such a derivative can then be expressed as a recentering of the velocity in the point. So the key point here is that we are taking derivative of log probability and not the derivative of probability, and this is one of the characteristics of the framework of information geometry. Okay, so now at this point we can take derivative with respect to points which moves along the curve, which corresponds to introduction of the notion of a moving frame. This allows us to define a velocity, which in our case is denoted by q star, and it is the derivative of the log probability, which corresponds to q dot over q. Okay. Next, we introduce covariant derivatives, which are needed when we want to move to accelerated dynamics. In this case, the covariant derivative is obtained in the following way. We represent our vector in the chart, which is the derivative, and then we send it back the vector to the tangent space with the transport which has been inverted. And this corresponds to basically a centering operation of W dot with respect to is expected value in the point, so in Q. So in this definition of covariant derivative, we have used the exponential transport. If we choose a different type of transport, we have a different type of covariant derivative. In particular, on the dual bundle, we will introduce the dual covariant derivative, where the transport is defined with respect to the Mishnah's transport, with the Mishnah geometry. Okay, we can also define a second statistical bundle, which is the tangent bundle of the exponential bundle. So in this case, we have 4 elements, again, the point and the vector, and then we have 2 other vectors, which are then parameterized in the same way through the exponential transport. So this is useful because it is useful for us when we want to discuss about acceleration. Indeed, in this case, what we will do is consider a curve, the velocity, and then again the velocity and the acceleration, and this corresponds to the proper definition of acceleration through the covariant derivative. So we have a formula, and we can express q star star, which is the acceleration along the curve, with respect to q dot dot q and q star. In this case, again, we have defined exponential acceleration because we use a transport which is exponential transport. If we choose the mixture transport for this representation, we can define the mixture acceleration in the dual tangent bundle. Okay, so now after introduction of all these elements which are part of the framework of non-parametric information geometry, we are ready to introduce the action integral and go in the direction of computing the Eulero-Lagrange equation to solve certain dynamics of the probability simplex. So our action integral is the integral between 0 and 1 of a certain Lagrangian function. This Lagrangian function is the function of a point and a vector. We can give then through the chart that we have introduced a representation of this Lagrange function as a function of u and u dot, and so we have basically a representation in the coordinates of our Lagrangian. We can then take the derivative with respect to the first argument, the second argument, and we can write the Eulero-Lagrange by taking the derivative of the Lagrangian with respect to the first argument and equal it to derivative over time of the derivative of the Lagrangian with respect to the second argument. And by solving the Eulero-Lagrange equation, we end up to a second order differential equation, which will identify a certain dynamic which depends on the choice of the Lagrangian. We can move from the Lagrangian to a Hamiltonian by using the Lagrangian transform. So basically, we can take the derivative of the Lagrangian with respect to the parametrization and to obtain a set of dual variables. And we can define the Hamiltonian and find the well-known equation which connects the Hamiltonian and the Lagrangian with respect to the inner product, which is our coupling that we have identified at the beginning between the two, the vector and the covector belonging to the tangent and cotangent space. So why this is useful? Because we want also to identify a Hamiltonian equation. Hamiltonian equation, again, in our framework can be computed explicitly, and we have the possibility to solve and obtain a system of differential equation also for the Hamiltonian equation to evaluate our dynamics from a different perspective. Okay, let's now introduce some example and see what we can do with all this machinery. So the classical example is the free particle, the simplest one. In this case, our Lagrangian is just a quadratic form which depends on the inner product in the point of W and W, so is the norm with respect to the Fisher matrix. And in this case, we can compute directly the Eulero-Lagrange equation, and we can rewrite a system of we can have a system of equation which can be rewritten in a system of first order equation of this form here that we can solve numerically and which give us a certain dynamics in the probability simplex. So up to now we have used Lagrangian, which is a quadratic form. We are interested in exploiting different type of Lagrangian, and in particular the Lagrangian which can be associated to a divergence function. So a divergence function is a function between two probability distribution, which is always positive or equal to 0 only when the two distributions are the same. We can move from divergence function to Lagrangian by associating a vector to a point, and this can be done, for example, with the use of the log map or its inverse, which move a point. So given a reference P, they can move a point in the tangent space of P through the use of the exponential map and the logarithmic map. So we have an equivalence between a couple of points and a vector point, and so we can rewrite basically our Lagrangian as a divergence between a point and the second point, which is obtained by representing the vector with respect to a mapping which, given the vector, allows us to identify a probability distribution. So we did this transformation, which is the one that identifies an exponential family. In particular, an interesting choice, or the most natural choice for Lagrangian over statistical manifold would be the one associated to the Kullback-Leibler divergence, which is a specific type of F divergence or Bregman divergence, and this gives us an explicit formula for our KL Lagrangian, which is easy to be computed because it corresponds to the cumulant. Okay, so now we can introduce a second example. Again, we are free particles, so in this case our Lagrangian consists simply of the divergence between Q and another point which depends on the vector W. Also in this case we can compute the Eulero-Lagrange equation and obtain an equivalent system of differential equation which can be studied and give origin to different dynamics. Let's see some example. Here we have the comparison between free motion of the quadratic Lagrangian and the KL Lagrangian in the simplex, same initial condition, and if we solve numerically the equation, we observe two different behaviors. In the case of the quadratic Lagrangian, we are approaching the boundary of our model tangentially, as you can see here with the orange curve. The associated velocity diverge, while in the case of the KL Lagrangian, all the velocity diverge. So, and we do not anymore converge tangentially to the boundary for P1 or Q1 in this case. Notice that the dynamics are behaving properly, so the sum of the Q is 1, so the trajectory belongs to the simplex, and the vectors tangent to the curves are always centering the point, so the expected value of V is always 0 over time. Okay, now let's move to a more complicated example. So we are now introducing an entropic potential. So our Lagrangian consists again of the quadratic form in the first case with the negative entropy, and the same here in the case of the KL Lagrangian. We have replaced the quadratic form with the KL and we keep the same potential. And in this case we can obtain a Eulero-Lagrange equation. We can solve them explicitly, in the sense that we can write explicitly the system of differential equation, and then we can solve the ODE numerically and obtain a different type of trajectory. As expected, in this case, the behavior is oscillating behavior, and it is an harmonic behavior. Again, the dynamics are staying in the simplex, the vectors are proper vectors, the expected value is 0. The dynamics for the same initial condition are different, and in particular, we see faster dynamic associated to the KL Lagrangian. Okay, so now, as I said at the beginning of the presentation, we are interested in application optimization. So how can we use this framework in optimization? Well, by introducing a time dependence, basically we can have dissipative terms in the equation which allow to have accelerated dynamics. So we follow here a framework which allow us to have a fully timed reparametrization invariant action by properly heading coefficient such that the reparametrization of time gives an invariance, and basically we are using a framework which is the one the one that is similar to the choice of the parametrization as it is done in Wikibon 2016. So we start from a KL Lagrangian, which is a specific type of Bregman Lagrangian. In the case we have introduced properly time scale coefficient, and we have a generic formula in which the coefficient appear here in front of F, which is our potential, as well as in front of the divergence and in one of the two parameters of the divergence. So we can explicitly write this damped KL Lagrangian in this way, which is easy to be computed, and it depends on the potential and depends also on the cumulant. We introduce, as in Wibisono 2016, proper ideal scaling condition, which allows to obtain basically for P2 and P3 the continuous time limit of Nestor of accelerated mirror descent and the cube regularized Newton method. So we are basically making a choice which allows us to obtain equations which are of the same type of the one discussed in Wibisono, even if in that context we are not over statistical manifold, but we are generically on Asian manifold. And we can solve this Lagrangian explicitly and obtain the following system of differential equation in which we have a dependence on the parameters for the scaling of time. Equivalently, we can define our Hamiltonian, and we can, by taking through the Lagrangian transform the dual derivative, express the corresponding KL Hamiltonian, for which we have associated dynamics, which can be rewritten in a very straightforward way by solving a corresponding system of differential equation, which gives rise to the damped KL Hamiltonian dynamic. Here there is an example. In this case, we have chosen as a function the entropy. So by the proper choice of the scaling, we are converging to the minimum of the entropy. So the minimum of the negative of the entropy, so the maximum of the entropy, which is in the uniform distribution. And these are the damped KL Lagrangian and damped KL Hamiltonian, which are basically equivalent dynamics, which however are associated to the different speed, in the sense that the KL Hamiltonian has a trajectory which is faster with respect to the KL one, but the type of oscillation are similar. This is the case in which we study the convergence to the optimum, and we can see that also in this case we observe a faster convergence for the KL Hamiltonian. This is an example based on the negative entropy potential, but clearly f is arbitrary, and we could choose other function for the evaluation of different dynamics or different optimization problem. Okay, so in this presentation we have introduced formalism for the study of evolution of probability density in a finite space. We have studied the continuous case of dynamics associated to Lagrangian and Hamiltonians, and we have introduced a different parameterization which allows us to have associated different differential equation, system of differential equation. In particular, we have found a way and a framework in which we can describe the proper dynamics and the proper mechanics of Lagrangian defined over statistical manifold. Future work includes the implementation of discretization schemes in optimization, which are compatible with the geometry of the space, and they allow us to move from the continuous dynamics to practical algorithm. And here there are some references of discretization scheme which is studied in the context of Riemannian manifold, which can be adapted to these settings. And of course we are interested in studying the other cases, not only the simplex, which are of interest in optimization. For example, the case in which we have some manifold or probability distribution of the simplex, parameterized with some natural parameters, for example, of the exponential family, or dynamics of the manifold Gaussian measure, which have interest in continuous optimization. Thank you very much for your attention. If you have any question about this presentation, feel free to send me an email. As I mentioned at the beginning, the material which has been used in this presentation is coming from a paper which is online on the archive. If you have any question or comments, just drop me an email. Thank you very much.